Hello? Oh, there we go. The reason is because people asked, why are these wrong? And, I could hear people saying, oh, yeah, they can see why it's wrong. But I knew that the answer why it was wrong was subtle and that I would neither be able to figure it out or explain it to you there on the fly. So on the subway on the way home, I came up to why these are wrong. All right? Remember what we're trying to say is we're trying to say that the problem can't be computed in quadratic time. So it's natural to say, every machine. The first one, what does it say? It says every machine kind of, if it solves the problem, then it takes more than n squared time, right? So that seems like it would be good, but it doesn't talk about the input. So what do we do with the input? We could say for every machine and every input, if it solves the problem, it takes too much time. Or you could say, for every machine, if for every input it gets the right answer, then for every input it takes too much time, right? So they feel kind of right in some ways, right? And so let me tell you the nuance of why it's wrong, right? So, I thought I changed the slides here. I guess I didn't. So I'm pretty sure on a slide I say, what are we trying to do, right? We're trying to say, for all m, who gets to choose? I'm trying to prove this is wrong, right? So if I'm trying to prove it wrong, it changes into an exists. And if it's an exists, then I get to come up with the machine, right? So I get to design the machine, and I have to design the machine so that the first thing is true and the second thing is false, right? Now, so for the first thing to be true, I need to come up with an algorithm that always solves the problem, right? And on the other hand, for this to be true, it has to be too slow on every input, right? So to make it false, what do I have to make it do? Does it have to be slow on every input? No, it has to be, no, does it have to be fast on every input? No, it has to be fast on one input, right? So that's why I'm going to define one special input, right? What's special about this input? It's an easy input. It's easy to recognize. It's long enough so that it has 10 characters. So 10 squared is 100. It gives me quite a bit of time to do things, right? So here, let's just fix that input. We don't even know what the problem is. We memorized ahead of time what the answer is, right? And now we're going to do code, right? Now I get to design the machine, right? Because my job is to design the machine. And what's my machine going to do? Well, I'm going to first check to see if my input is the special input. And that doesn't take me, that only takes me time 10, right? And then, if it's the right input, I'm going to give the answer. And now I just have to output the answer because I memorized it, right? Is everybody, right? Now, otherwise, what I'm going to do is I'm going to solve the problem quite leisurely, right? But since the problem is computable, we're good, right? So now what do we have, right? Now we have a machine such that this is always true. It's always solving the problem. And the other thing is sometimes false, right? It's false at least once. And if it's false at least once, then that's wrong. Right? Everybody got that? In fact, what we're going to get you to do next, is to take the negation of that. And if you take the negation, it's going to get something much more like, for every machine, if it always works, then at least once it takes too much time. Right? That would be closer to what we need. Right? It could be it could be a problem where on even inputs, it's really easy to compute, and on odd inputs, it's really hard to compute, right? Like, for example, here's a problem. I give you an integer I, and I want you to factor it. Well, if I is even, that's pretty easy, right? But if I is the product of two primes, then trust me, it's hard, right? So we can't say that it's always going to be hard, right? Everybody good with that? All right, we're gone with that. Though I did have other things. I should find out where they went. Maybe I deleted them. Now we're doing models. And our goal is to work towards Turing machines, but we're going to do some chat before that. All right? So ask questions, give me feedback, all those various good things. All right, so what historically Euclid is credited for coming up with the first algorithms. And he was very religious, and one of his algorithms was the GCD algorithm, which I was about to say we're going to cover, but I'm wrong because it's in 3101. We'll cover it. So wait for that. And there's the loop invariant for the GCD algorithm, and he said it was good, right? Now, I question, remember historically, the Egyptians were building pyramids. So they must have been doing some thinking. And so I'm not sure why he gets the first algorithm, but I think he gets the first one in terms of, right, we're in some state, we do some maintaining, some loop invariant, I don't know. Maybe, I don't know what the Egyptians were doing before him. But anyway, he's credited with the first one. So, and of course, everything they did had to do with God. And so they were definitely had the belief that everything you could want to do, God can do, so clearly it could be done, right? So they differentiated between two types of algorithms. Those algorithms for which they knew how to compute it, and those algorithms which they didn't know yet how to compute, but surely it could be done, right? And then we jump, all right, and what did Euclid did? He proved that GCD, greatest common divisor, could be done, right? So let's move through time here a little bit. In 1801, you might know this already. It's all pretty cool stuff. In fact, I've seen these at museums, right? They started to build looms that use punch cards. And this machine here had 24,000 punch cards, right? Which tells you when to lift the thing and when not. So you got a picture of a rose, right? So that's pretty cool, right? And that's kind of computation-like, right? And then Charles Babbage designed this thing, and he got some woman to fund it, and they built it, and it really would have been a computation machine. It had all these dials, and if the dials turned, they would have computed things. They just couldn't get them to turn, right? There were just too many dials, pushing too many dials, and they didn't turn. But otherwise, it's cool, right? And then the census comes along, and they used to do the census by hand. And in this year, they made punch cards, which you punch out how old you are and how many people are in your family, and then you run the punch cards through a machine. And that was a big step. Did anybody watch the movie Kinsey Report? He went around and did the same thing and asked people questions about sex, and he put them on punch cards. About, I don't know what year that was. All right, now we're jumping further. Right now we're doing, I don't know, he's just before World War II. Hilbert starts to ask the question. In fact, Hilbert has a list of problems. There was a conference in Paris in the 20s, I think. I don't know when it was, in which he listed a bunch of problems. And it was a good list because he nailed what were the big problems in computation that were going to either not be, so today they're either not solved or they opened up whole fields of mathematics. So it was really a good list. And one of his questions was, are there uncomputable problems, or can every problem be computed, right? And it's 1900, so it was even earlier than I thought, right? So in order to prove that an algorithm, there is an algorithm for something, right? You just need to come up with something that solves the problem, and everybody says, yes, that's an algorithm, right? But if you want to say a problem doesn't have an algorithm, then you need a very clear definition of what an algorithm is, right? For example, the following is not an algorithm. Do this, this, and this, and then say miracle, and then you have the problem solved, right? That's not an algorithm. So you have to define what that means, right? And so then, actually, we're going to say that Turing came up with the first model of computation. And, the more I study Gödel, which we're going to later do Gödel's incompleteness theorem, the more I give Gödel credit. Gödel came first, and he had a model of computation based on recursion. And in the end, it didn't actually compute everything. And is it this course? There's some course where I prove to you that doesn't prove everything, and it might be in this course. I don't remember. We might cover that. It can't compute Ackermann's function, if you know what that is. But anyway, Turing, people give credit to Turing for the first model of computation. All right? And Turing then went on. Then we can talk, as soon as we define a model of computation, that defines what an algorithm is, right? We say a problem is computable if there's a Turing machine that can compute it, right? There's a definition. And this is way before they had computers, right? So this is all math. This is all esoteric math that everybody thinks is useless, right? And then he managed to prove that the Hopfing problem is uncomputable, right? And again, we can say he was brilliant, but really, he's just doing tweaks on what Gödel did. So I like Turing, but I like Gödel even more. All right? Did you guys watch the movie about Turing? What was it called? Imitation Game, right? Because meanwhile, he's also while he was Hilbert's grad student, and he was also working in the war room trying to break the codes for the Germans, and managed to do it. And so that's all worth knowing. Anyway, right? So Turing machine, is it a practical machine? No, it's not, right? No one's ever going to write code in the Turing machine. So why are we doing it, right? Well, back when they were doing proofs before machines, they wanted the simplest proof system that could prove everything. It's all about what's the minimalist we need. And so this is kind of cool because it's the minimal model of computation from which you can prove anything, right? And in some ways, it's like when I was an undergrad, I got jobs in which I wrote code in machine code. But should you ever write code in machine code? No, you write them in Java and we compile it down. Because why? What's the difference? Is now we have better compilers, right? So similarly, you don't want to write code in Turing machine, but I'm going to try to teach you not how to write code in Turing machine. I'm going to try to teach you how to take your Java code and compile it into a Turing machine, right? So we're going to work more on teach. I know when Eric, I've seen his tests. He made people write Turing machines. Instead, our test, I'll tell you what's good. There will be a question in which I give you a piece of pseudocode. It won't be Java code. It'll be pseudocode. And you'll have to compile it into, and so you won't have to do any thinking. It's just you'll be a compiler. You'll compile it into a Turing machine, right? And I think it does help you think in terms of there is something that we want you to learn here. And it's thinking about computation not as Java code, but as I'm in this state. What state am I in? What is my set of states? Now if I'm in this state, what action do I take? So now I'm in this other state, right? And it's similar to what I was spoken. I don't know, we haven't done loop invariance yet here, have we? I'm religious about loop invariance, right? The loop invariant is more or less says the same. I'm in this state. What's true in this state? I'm not thinking about actions. I'm thinking about what's true right now. I have a loop invariant. What do? I take an action that puts me in another state, and I want my loop invariant still to be true, right? So it's kind of, we're just trying to work on focusing on those ways of thinking about things, all right? So in fact, these are states, and we're going to transition from state to state as we have lots of memory. And you might be thinking, why did Jeff do so much first order logic? Right? We're going to need so much first order logic, right? We're going to do there exists a machine. Well, when you say there exists a machine, we're talking at compile time, right? At compile time, there's a fixed number of states, right? It's a finite state machine. What does that mean? It means at compile time, there's a fixed number of states. But then we need to say for all inputs, and the inputs could be much, much, much bigger. We want to say for all inputs, right? So then we need an arbitrarily long tape so we can use more and more memory, right? So the nuances between how, is this an infinite tape? We're going to call it an infinite tape, but in finite time, you only can use a finite amount of it, right? So you could say that this is a finite tape and this is a finite number of states, right? But they're different, right? One is in the exists, the machine, and one is in the for all the inputs, right? And so if you're going to get those nuances, I wanted you to really get there exists the machine for all inputs kind of stuff, right? Everybody kind of with me here? All right, so we do some more history, right? Then they started building machines, right? That actually worked. And these tubes, they're vacuum tubes where if this guy has electricity, it wants to jump way over there, but it can't quite jump. But if this has electricity too, then this one starts to jump and jumps further. And so you get an AND gate. That if we have something here and we have something here, we get an AND gate. And then you build OR gates and NOT gates out of these tubes, right? And then they build this first machine, right, which was filled rooms and rooms, right? 17,000 tubes. And then they build this, Turing's in the movie at least, didn't seem to have tubes, it seemed to have gears. But anyway, they built these things, and it was good, right? Evidently, a tube failed every 2 days. It took them 15 minutes to find where the tube was burnt out. And the idea of a computer bug, right? It was a moth underneath one of these tubes. And if you go to the museums in Washington, D.C., you can see the original bug. It's very exciting. It's a moth. All right? And then, of course, they built transistors in the 50s. And then, then they built, this here. Right? Look at those. What is that? That is one AND gate. Right? When they first built them, that was one AND gate. So it's a big improvement over that. So people were excited, right? But now, right, they started building these things. And how many AND gates are in there now? Anybody know? I don't even know. It's billions, trillions, right? We can get a little stick that has a trillion of them. I don't know. Lots. So that was exciting. All right, so now let's go back to Turing, right? This circle is what can be computed by a Turing machine, right? But this circle might be what can be computed by a recursive program that Gödel was coming up with, right? Versus we could have this as the circle, what can be computed by a Java program, right? And now we want to start proving some theorems. Can do they prove different things? Can they solve different things, right? And we can easily prove which one. The exact one that Gödel did couldn't do Ackermann's function, so they weren't quite the same. But you give it a little extra power, then it can do it, right? So every model, people kept trying different models, and surprise, surprise, you can have really dumb models. In fact, you can have a model in which that you have, say, 4 stacks of blocks. And all you're allowed to do is take a block off or put a block on. But you can look at how many blocks. You can't even look at the blocks. You know whether the blocks are empty or not. And based on that, you put another block or take a block off. Simple machines. And they're all Turing equivalent. Right? So are they equivalent? So some guy, Church, I don't know who he is. All I know is he said yes. He has a conjecture, right? And the reason it's what's the conjecture? It says all reasonable models of computation are equivalent in terms of what they can compute, right? And so why is it a conjecture? Well, how do you define reasonable, right? If your definition of reasonable is that it's Turing equivalent, then by definition they're all equivalent, right? So, do you have a question?
A question about the previous slide.
Yeah.
Talking about how small AND gates could be.
Yeah.
But there should be a point because AND gates they work through electricity.
Yeah.
They get smaller than an electron.
Yeah, exactly. We're definitely, Moore's law, every 2 years they get half of size. We're definitely banging up against that, right? All right? So this is saying we can define, in fact, there's some course I taught for something. And we define all these models of computation, and we prove that they're all equivalent. All right? So we're going to do a little of that with a little bit more hand-wavy. Right? And in fact, how do you prove? Anybody want to tell me how you prove that anything a Java program can do, a Turing machine can do? What does the proof look like? In Java? Anybody else? We need a compiler, right? We want to prove that anything that can be done by a Java program, right? You give me any Java program. How can I prove there's a Turing machine that can do the same thing? All I have to do is give you a compiler, right? Takes a Java program, compiles it into a Turing machine, right? Which might be what you're saying, but right? All right, so and now here's an extra caveat here, which didn't happen until my father came along. They started talking about polynomial time. So they had the conjecture then, any reasonable model of computation, they're going to have they might have different running times. This Church was just saying, if you can compute it, you can compute it. And if you're doing this model that I was talking about here, it's not reasonable, right? In the sense of what it can compute is reasonable, but its running time won't be the same. So now it's saying any Turing machine any machine that can talk about bits, right, instead of counting, right? If all you can do is plus or minus 1, then that's not as good as if you can divide by 2, right? So then are equivalent within polynomial time, and then we're going to see, oops, they came up with quantum machines. That really rocked people. Is a quantum machine a reasonable model of computation? No, but physics seems to be doing it. And it can do things in poly time that normal machines only can do in exponential time as far as we know. Right? So, all right, everybody good? Everybody going to put up their hand when they don't understand something? Yeah, yeah? Oh, you were just practicing. Excellent. Thanks. All right, so really we're going to start doing hard things, right? So ask when you don't understand things. All right, so I think we did this already. What is a computational problem? For each input, it tells me what the output is, right? Sorting. What's a language? A language is a a computational problem where every answer is yes or no, right? So here's an example. Is the input sorted? I give you an input. You tell me yes or no, it's not sorted. Another example is English. I give you a sentence. You tell me, is it an English sentence, or is it bad grammar, or is it in French? Right? Yes or no. What's a machine, an algorithm, a program? It's a set of instructions that if you give it an input, it'll crank forward and it'll either halt or run forever. Halt and give you an answer, right? What's the model of computation? Right? We've given some examples. Turing machine is a model of computation. Java is a model of computation. Those little blocks over there was a model of computation, right? What does it do? It tells you what is a legal algorithm, right? In the Java model of computation, a legal algorithm is a Java program, right? All right, so here we're defining model of computation because we're going to be defining a bunch of them, right? What's a model of computation? It tells me one thing that's absolutely true is that every algorithm needs a finite description, all right? When we prove that the halting problem doesn't have an algorithm, we're going to use nothing about Turing machines other than that every algorithm has a finite description. That's all we're going to use, right? Oh, one more thing we're going to use. And that given the algorithm, it's well defined what the machine does on an input, right? Finite description, deterministic output, right? That's what we're going to define. All right? Finite description, and we have to say, if you were to pause the idea of an algorithm is it's cranking along, right? So there's a sense of time. And if you pause the algorithm, we can say, what state is the machine in, right? So if you're running a Java program, right, what state is the machine in? Here, the state is you got a bunch of blocks piled up, right? Meaning how do you store data, right? Which line, do you have a line of code? Right? Right? And then, given I'm in this state, right, tell me what state I'm in, then you have to tell me what are the legal actions that I'm allowed to do. Am I allowed to say, by miracle we have the answer? No. Am I allowed to say, add one more block here? Yes. Am I allowed to say, cut the pile of blocks by a factor of 2? In this model, I can't. Right? So what am I allowed to do? How do you specify the input? How do you specify the output? These are all model of computation kind of things. Right? And then once you define the model of computation, then it's reasonable to ask for which computational problems can I solve within this model of computation, right? And to solve it, ideally for every input, the machine will halt and give you the right answer, right? So these are reasonable questions. And we're talking about the theory of computation. This is what we're talking about, right? All right, so here, Java programs, right? How do you specify it with code? What's the current state? Tells you the values of all, what your memory is, right? The values of your variables, your data structures. Tells you what line of code you're on. That's the state, right? What is the legal actions? Legal lines of code of Java, right? How do you read input and output, right? You do it from a file or from the keyboard. And so here are various models of computation. I think some of them we might spend a page on, but we want to show that they're all equivalent in terms of how they compute, what they can compute, right? And I just added this on the subway here, a little caveat. Well, the running times might be different. Right? So let's do what we just talked about, right? This is going to say, if you can do it from a Java program, how do you know that you can do it with the Turing machine, right? And And here, we can write it down as first-order logic statements, right? Right. The first one says we have the set of problems that computed by a Java program, right? So here, Java. These are all problems that can be computed by a Java program, right? And here are all problems that can be computed by a Turing machine, right? And we want to ultimately prove that these two sets are equal. And how do you prove it? We're going to prove it in two steps. First, we're going to prove that the set of Java programs is a subset of the set of Turing machines, right? We're going to prove that this doesn't happen, right? And why doesn't it happen? It doesn't happen because for every problem, if a Java program can do it, then a Turing machine can do it, right? And what does it mean for it to do it? There exists, right? If there exists a Java program such that on every input it gives me the right answer, then there exists a Turing machine that on every input it can do the right answer, right? And then we could say it another way, and converting from one of these to the other, I've had people do in grad class, and maybe if I teach 1090, I'll get them it's a 1090 sort of question, right, to prove if one of these is true, the other is true. Right? This other one is slightly different, right? This one's talking about computational problems, right? And this one doesn't talk about computational problems. This one's saying, for every Java program, you give me a Java program, I can compile it into a Turing program such that for every input, they give me the same answer. Right? People follow that? And your intuition, that should be those are the same, and we could do 1090 to prove that they're the same. Yeah? Oh, no, then we're going to do the other direction. Right? You have to go both directions. Right? So everybody get this? And how does the proof go? Right? All right, this is just saying, if a boy can do it, then a girl can do it better. Right? If a Java program to do it, then a Turing machine can simulate it. Right? And so, I thought we were going to have a proof here, but the proof is a compiler. Right? All right, so now let's talk about other models of computation, and we're going to do this for two reasons. One is to give you examples of computation and examples of how you prove that they're equivalent. And the other reason is we're continuing in the history of computer science. All right? So in the 70s, people were all excited about writing code, and their code were all go-tos. All right? So what is a go-to code? Right? Here's an example of a go-to code, right? You can have an if go to line 1. Right? Everybody with me here? And that's kind of what machine code does. In fact, they started by coding by hardwiring wires, and then they got machine code. Well, then they got punch cards, and the punch cards were all machine code, right? And the punch card would say, if, go to, right? That's what a punch card would say. And so that's what their code was. And if you've ever tried to write code like this, it can be very crazy. And if you try to read someone else's code, it's crazier, right? Have you ever heard the word spaghetti code? Right? This is spaghetti code. Things are just going every which way, right? So that's great, right? And then just about the time I got to undergrad, right? In high school, we were still doing machine code and punch cards, but in '82 at Waterloo, we were doing Fortran and loops, right? So then they said, right, you can't do go-tos, right? The rule is no go-tos. Instead, all you can do is while loops and if statements, right? Everybody with me here? So these are two models of computation, right? This one doesn't have while and if statements. This one doesn't have go-tos, right? And we want to know, do they compute the same things, right? We want to know that. So, because clearly, if somebody had to propose, let's limit herself never to have a go-to. We have to have a good reason for that, right? And the reason is so your code's not so spaghetti and we can prove things about it better. And but to do that, they had to prove that they're not limiting the power of computation, right? So anyway, what are they doing instead, right? They're doing things like these for-to statements, right? In fact, this was 90s. We didn't have anything that complicated in the 80s, right? But you know what I'm talking about, right? So do they have the same power, right? Do they compute the same things, right? And so again, we're proving those lines as we did before, right? And there's the line. We have to do it in both directions, right? And so here, if we're going to formally prove this, right? We're going to formally prove a first-order logic statement. We want to prove for every go-to statement there exists a loop program. For every loop program, there exists the go-to program. How do you prove that, right? We do our prover-adversary thing, right? We say, let P be an arbitrary loop program, right? Because we're saying for all loop programs, we can get a go-to program. So here's a loop program, right? Now it's just a little example, but it's an arbitrary loop program. Can we write go-to to simulate it? Yeah, clearly, right? It's pretty straightforward. Every loop gets replaced by a go-to, right? So that's easy, right? Everybody with me here? Now the other direction is harder, right? Now you've given me an arbitrary go-to program. And this could be spaghetti code all over the place, right? How do I compile it into a program that doesn't have any go-tos, that's structured, that has a nice, neat loop, that you're going to do this loop for a while, and then you're going to do this loop, and you'll exit. Maybe you'll have inner loops, right? But it's very structured, right? Any idea how to do that? My bet is not, right? And the reason I'm going to bet not is because it's actually a deep idea. All right? All right, so there's an arbitrary go-to program, and let's see how we're going to go over, right? And, right, we're designing our loop program. And you might not know me. Let me introduce myself. I like loop invariants, right? So I'm going to have a loop invariant here, right? And what we're going to do is we're going to have one big loop with one big loop invariant. And what is my loop invariant going to be? Well, every time you do one of these actions, I'm going to go around the loop once, right? And when that's not my loop invariant, that's an action. What's true at the top of the loop is that when you're at the same point, I know my variables all have the same values, right? That the two computations, the loop invariant says they're going to go together, right? So my loop invariant, which is a picture of what's true right now, is going to say, hey, I'm on some line of code here, and whatever values it has, I have the same values, right? Right. So, and what do I also know? Not only, it's basically I know the state of that machine, right? I know the state. So I know the values of the variables. I know what line it's on, right? So it's telling me I know the state, right? Everybody good? And somewhat, that's what we're going to be doing this whole course, is you can think about your program as a bunch of actions, or you can think about it as a bunch of invariances. I'm in this state. That's an assertion, right? That's a picture. And then I take an action to get into another state, right? So in some ways, we're converting from this is just action to this is a sequence of assertions of what state you're in, right? So that's why I said that there was a deep idea there, right? And so now, right, now what do we do in the loop? Here, we initially say we have to establish the loop invariant, right? We establish the loop invariant. Well, this program establishes it in line 1. We set all the variables to their initial values. And when do we exit? We exit when we know we're done somehow, right? So that's our one big loop. And what are we going to do? Well, I told by the loop invariant I know what line we're in, right? So if I'm in a line 11, what am I going to do? I'm going to set x to equal 0, and I'm going to go to the next line, right? That's just an if statement, right? And if I'm in line 38, what am I going to do? How do we assimilate a go to? All I have to do is say, now I'm in line 18. Right? Does that make sense? And then if I'm in line 99, then I specify that we're exiting. Right? Everybody good? Can you see how, I mean, I did a little hand wavy, but I more or less proved that these guys are the equivalent. Are people following? Everybody's good? All right. Do these have the same? Now, yeah, we did that. Here's a little question that might be on the homework assignment. I don't know where this is. This might have been from a different course. So somewhere there's this homework question. Question is, here's a problem. Can every computational problem be done by a single loop, or do there exist computational problems that require two loops? To find exam question, I should put this on exam question. Right? Are there computational problems that require two loops? What do you think? Is it required, right? Are there computational problems that can be solved by two loops but can't be solved by one loop? Come on, guys. Come on, guys. What did we just do? You just compile it. Tell me your favorite program that you claim can be done with two loops, but that can't be done with one loop. Right? Write it down as a first order logic statement. Right? Here we're saying there exists a problem such that there exists a two-loop program, right? And there does not exist a one-loop program, right? Is that true? And I claim it's not true. Why? I'm claiming for all problems, right? If there exists the two-loop program, well, you have to muddle around. You have to be good at 1090. You have to translate this. And more or less, we can translate it into if there exists the two-line program, then there exists the one-line program, one-loop program. Right? Everybody getting the first-order logic? Right? Now, when I'm standing up here and you guys aren't getting it, then I'm not really sure. Are you not getting it because you can't do this first-order logic part? Or you're not getting it because you can't solve it from here, right? So everybody see that this is what we needed to do? To prove it's not true, right? To prove it's true, you have to give me a problem that we can solve for two loops but can't be solved for one loop, right? That's the question. So to prove it's not true, you have to prove that for every problem, if you can do it for two loops, you can do it for one loop. Right? Everybody getting that part? Now, how do we prove this? We do it by the game that I've been teaching you. Right? How do you prove it? Give me an arbitrary problem. Right? Now we have to prove A implies B. So, assume A. Assume there exists a program that can be solved with two loops. Right? So here it is. Here's code. It has two loops. Right? Now, I have to come up with a program that has one loop. Here it is, program with one loop. Then I have to prove they do the same thing. Right? Now, anybody want to tell me how I get from here to here? Yeah? Did you hear that? I told you how to do it. I told you that any Java program can be converted into a GoTo program. Right? I told you that. And I told you that any GoTo program can be converted into a one-loop program. Right? That should tell you, right? That should when I did that, you should say, oh, that's cool. That tells me something else. That tells me every program can be done in a one-loop program. Right?
So just to get rid of the second loop, you can just replace it with using GoTos.
Well, did you understand how we took code and converted it into GoTos? That was simply, you have a loop, and you replace the in loop with a GoTo. I mean, that's just nothing. The reason you didn't understand it is because it was nothing. Right? And then, did you understand how to convert the GoTos into a single loop? All right, well, let's do that again. Maybe people aren't getting the nuance here, right? Here's arbitrary GoTo code, right? I'm taking arbitrary GoTo code, and I'm going to convert it into a program that has a single loop, right? So, what's my loop going to have? At the top of the loop invariant is going to tell me that it knows the state that this machine's in, right? It knows the state. And what does that mean? It knows the values of all the variables, and it knows what line of code it's on, right? And remember that, because we're going to come up with that theme over and over again, right? We're going to be converting some code like this into a Turing machine, right? And how do we do it? Well, the Turing machine is going to be in some state. And the loop invariant will be that the Turing machine, the state it's in, knows what state your algorithm is in, right? So what does it know? It knows the values of all the variables. It knows what line of code you're on, right? So that's what this program knows, right? This code is has run for a while, right? We have to prove that these two, how do we prove they do the same things? Is we prove as they run for a while, they're following each other, right? So what that means is when this is in some state, this guy should know what state he was in, right? That seems reasonable, right? If I want to simulate you, I need to know at every point where you are, what you're doing, right? And I have to then say, oh, if he's here, I'm going to simulate his steps. So he takes a step, I take the same step, right? Does that make sense? So what we're going to say is this code will know where this guy is, and then when this guy takes a step, he's going to take the same step. Right? Does that make sense? So how do we take the same step? Well, if this guy is setting x to equal 0, then this guy knows which line he's on. Right? He knows that code is on line 18 because we have a variable line that will have the value 18. Right? And then what does this code do? It says, oh, it wasn't 18. Sorry, it was a line 11. I saw an 18 there and I got it confused. Right? It says if I'm on a line 11, and maybe that should be a double equals. You know, I was never good at coding. Right? If it's 11, then what do I have to do? Right? Well, what do I have to do is I have to set x to equal 0. And then what's my next line of code? It's 12. Right? Everybody got that? And similarly, if this program is in line 38, then what do I have to do? I have to go to line 18. Right? Everybody kind of getting it better this time? Right? So this is an example where I'm putting something on the board, on the slide here, and maybe you're kind of hearing what I'm saying, but you're not getting the point, right? And so if you're feeling hey, maybe I understand your words, but I'm not getting your point, right? Then slow me down so we can get the point, right? And somehow this two loops to one loop was helpful to think, am I actually getting the point, right? All right, so everybody get this now? So now you can imagine if I have a program with two loops, then I convert it into gotos. And I don't even do it. I could do the same trick straight from the two-loop guide, right? Right? Now, is this a pretty program? No. No. But, you know, I have written code that looks like that, right? Because sometimes it's good. I kind of call it, sometimes I think about it as an event-driven program, right? What does that mean? I'm at the top of the loop. I've handled everything that's come to me so far, right? I know the state of where I'm in. And then some event happens, whatever that means, right? Maybe somebody pushed the button on the elevator or some event happens. And in this case, right, we get another line of code. And then I have one iteration which kind of handles that event, right? It's a way of writing code, right? Everybody got that? In fact, the first couple weeks of 3101, we're going to have one loop. And what is that? I have a loop invariant. I maintain the loop invariant. Those are all programs that have one loop. Yep. Here? You know, I'm going to have to say that my immediate answer is I don't know, right? And when they teach you in 1090, they teach you the mechanical ways of going from one line to another. And I was never a good rule follower, right? I was good at the intuition, and so I would just write things down, right? My intuition told me that this and this were the same. And if you don't believe me, then we're going to have to go down and formally do it, right? So it might be, I don't know whether it interests everybody, but you know, here we got A and B. Well, this sort of says A implies B, right? That's a P. A implies B. And what does that sort of say? It's not true that A is true and A is true and B is false, right? That's what this means. It's not true, right? So now when we went from here to here, now we're going back in the other direction, right? When we go the other direction, we want to get rid of the negation, right? So now we want to say there exists a P since that this is true, right? And this is my exists, which is my exists, right? And this is my not be, which is my not be, right? So did I do that in my head? You know I didn't. You know, it was all, I make it up as I go. People complain that when I teach, I make things up as I go. Does that answer your question? Right? I mean, we could formally do it. And I mean, that's the trick of formally doing it, right? Right? So in fact, I could flip this to say, for all loop programs, it doesn't work, right? So there are things where for all is flipped to exist, and it gets hairy. And so how should you do it? Well, the truth is, if you have enough time, you should both think about it intuitively, and you should mechanically check it, right? So I've been having I don't know if you know George Shalakis. He and I have been having arguments about 1090, and I say I want my proof system to follow my intuition, right? Because I rely on my intuition. Maybe did you do Myers-Briggs? You know, there's P's and I don't know all the letters. You know, I'm relying on my intuition, and that's what I did. And George is not an intuition, right? He says intuition is garbage. It'll get you lost, right? You have to go by following the rules. So, I don't know. Everybody good with this? Should we move on? Did I frighten you there? Right? Right? So there is this difference between following rules and intuition. Right? And in my life, my math intuition has been pretty good, and sometimes it doesn't work out. You know, I'll come to my advisor's office and say, I have these great ideas. And she said, where did you get those from? I don't know. You know, the goddess gave them to me. Let's see if they work. And sometimes they work, and sometimes I did it wrong. Right? All right. So, right. So now it still boils down to I want to be able to prove things. Right? I want to know my program works. Right? How many highs get printed? Well, hopefully you can figure that out. You know, everybody will know that it's 10-ish. Right? Is it 11? Is it 9? Is it 10? Right? We get a little nervous. Right? So that's when we bring in loop invariance, right? And loop invariance, I was not taught loop invariance when I was an undergrad because it wasn't around yet, right? So what's loop invariance? It's a paradigm shift where we're thinking about, instead of code, sequence of actions, we're thinking about a sequence of landmarks. I'm in this state, now I'm in this state, now I'm in this state, right? And, right, so, this is what I just said. Right? We can think about code as a sequence of actions, or it's a sequence of landmarks. And those landmarks are, I was born in Washington, I went to Waterloo, I went to U of T, I went to Berkeley, I went to York. That was my life. Right? Then I'm going to retire somewhere. I haven't gotten there yet. All right, so now we want to understand how many highs get printed. Right? So, we're going to focus on the sequence of states instead of the sequence of commands, right? So what this says is I'm going to have a loop invariant that tells me when I'm in the middle of the computation what's going to be true, right? And in this case it says I'm going to have two things that are true at every point. One thing that's true is I'm going to have a variable x. And the other thing that's true is I've printed out some number of highs, right? And what my state's going to be is that I'm still on the path as long as those two numbers are the same, right? So that's going to be what I always want to be true. X, my value x, is going to be the same as the number of highs I printed out. Everybody got that? Right? And then what does this say? This says if the precondition is true, you know, I'm starting from home, I'm trying to get to school. My precondition is true. I do that initial code at the beginning. I can establish the loop invariant, right? So it's all, how do I go from state to state to state? And somewhat, you might think, hey, you're doing 3101 again. You know, you always catch me accidentally teaching the wrong course, right? But we're going to have to build the Turing machine. Right? That's this course. And to build the Turing machine, I want to know I got a loop. If you want to have a loop, you need a loop, and you need to know what's true at that loop. You need to know how you establish that and how to maintain it. Right? So here we're going to say, how do we establish the loop invariant? Well, all I have to do is set x to be 0 and print no highs, and we're good. Right? And what we want in that top code is don't try to think about the whole computation, because if you do, you'll panic and you'll drown, right? So instead what you need to do is, how do I establish the loop invariant in the easiest possible way, right? And people who have been in class from me, I say this in every course I ever teach, right? Some of you are in my 3101 and you're all falling asleep right now, right? So how do you establish it? You set x to be 0, because 0 is a good number. Right? Don't forget 0 is a good number. You said 0, you do know 0 highs. Right? Everybody follow that? And then this says, I fly in from Mars, I say, I'm at the top of the loop. I don't know how I got here. I don't know how many times I've gone around. Maybe I didn't go around at all. Maybe I just landed here. Right? All I know is that the loop invariant's true. All I know is that the number of highs printed so far is the same as my value x. And what do I need to do? I need to take some step that makes progress. Well, what's for progress? We got to print more highs, right? And it maintains the loop invariant. So what are we going to do? We're going to print one high and we're going to increase x, right? Everybody see that? Maintains the loop invariant while making progress, right? And then we got to get the post condition, right? This is post condition is that we printed 10 highs. So we say, well, we've dropped out of the loop. And when we drop out of the loop, we know two things are true. We know the loop invariant is true because we've maintained it. We know the exit condition is true because we exited, right? So we know that x is the number of highs printed so far. We know that x is 10 because we exited. So we conclude the number of highs printed so far is 10. Right? Everybody following that? That's the first third of 3101. Right? And that's what we're going to, when we build Turing machines, we're going to be doing this. All right? And now, actually, I lied to you. This proves that if the program terminates and the input meets the precondition, then we'll get the postcondition, right? We haven't proved that the program terminates, and if the input doesn't meet the precondition, then who knows what happens, right? Try to be polite. Everybody good here? So here again, we're talking, right? Here's the various data structures, right? We have Java, we have object-oriented stuff, and now over here we have another model of computation, which is machine code, right? So here's Java versus machine code. Do they compute the same things, right? We're going to do the same thing here, right? Given any program, if it computed by a Java program, it can be computed by machine code. If it can be computed by machine code, it can be computed by a Java program, right? So everybody know how to do that? Right? There's memory, right? So if it can be computed by machine code, can it be computed by a Java program? Well, surely you can write a Java program to simulate your machine code, right? Surely you can do that. So yes, proof, it's just easy, right? How do you go the other way? You have a complicated Java program. How do you prove you can do it by machine code? You get a compiler, right? That's the definition of a compiler, right? And proof by compiler. And later in this course, we're going to be talking about context-free grammars. And I have fights with everybody. One of the fights I've been having with Frank for the last 25 years is he thinks we shouldn't teach about parsing. And I think it's the best algorithm ever, right? And if we couldn't parse, we wouldn't have computer science, right? So one of the algorithms I do love is how do you take a Java program and compile it. And I don't know if I told you, my son came in grade 10 and we wrote a compiler, right? So it's not very hard, right? We could do it in 3 days, right? And those were only an hour, in the evening. It's not like we all had jobs. All right, so what are we doing now? Oh, now we're defining Turing machines. All right, now we're ready for Turing machines. Any questions?